Benvenuti, sono Barbara Gallavotti, sono una giornalista scientifica e sono qui per introdurvi Jim Al-Khalili, fisico nucleare teorico, saggista, autore e anche scrittore di molti libri di successo che vanno dalla storia della scienza, pensiamo La casa della saggezza, l'epoca d'oro della scienza araba, a libri di fisica quantistica. La sua ultima opera, Il mondo secondo la fisica, è stata pubblicata in italiano da Bollati Boringhieri. L'ho letta, ho avuto questa fortuna, ma mi sono accorta che abbiamo un problema perché gli organizzatori del CICAP Festival mi hanno detto che questa intervista deve durare 30 minuti, ma non hanno specificato a quale piano dobbiamo misurare questi 30 minuti. Professor Al-Khalili, benvenuto. Ci dica, possiamo stare tranquilli? Quanto è grave questo problema?
Well, actually, the problem is fascinating. I wouldn't say it's very bad, but it exists. What you are, of course, referring to is the conclusion from Einstein's theory of relativity, which we have known for over 100 years now, which is that gravity affects time. It affects how fast time passes. Now, for most of us, certainly for non-physicists, we think of time as absolute, as independent. You know, we have different time zones around the world, but that's just humans' invention to make sure that we all have the same sort of hours of day. But we think of time as ticking by some cosmic clock, ticking by seconds, minutes, hours, years, the same everywhere in the universe. Einstein showed that this isn't true. And in fact, gravity, the force of gravity, which we learned from Newton, which was studied by Galileo, isn't this simple force that pulls us to the ground, keeps the moon in orbit around the Earth. Gravity affects both space and time. So gravity slows time down. Now, on Earth, the closer you are to the center of the Earth, the stronger the gravitational field is. And so the slower time will run. Therefore, your point about which floor we should be discussing, talking about this and what is 30 minutes, this is true because the higher up you are, the further away you are from the Earth, and the slightly, very, very slightly weaker gravity is, and therefore time runs a little bit faster because gravity is weaker. Now, of course, this is a tiny, tiny billionths of a second difference. We would never notice it. We do notice it, though, in technology. And this is why it's interesting. This is why it's important, because GPS satellites, which we use with our smartphone that tell us where we are in the world, they make use of information from satellites. And those satellites have to measure the same time, rate of time. Yeah, a second has to be the same on the satellite as on Earth. But it's not, because the satellites are further away from Earth and time can therefore go faster. So we have to artificially slow down the clocks on satellites, sure they're synchronized with Earth. So Einstein's theory isn't just some crazy idea from science fiction. It is real, and our technology depends on it. And I find this absolutely fascinating.
Grazie, professor Al-Khalili. Ma ora andiamo al cuore della fisica. Perché nel 2012 al CERN è stata annunciata la scoperta del bosone di Higgs ed è stato un momento di grande eccitazione perché questa particella era cercata da mezzo secolo, da 50 anni, era l'obiettivo principale da raggiungere per i fisici sperimentali della fisica delle particelle e anche per i teorici per avere delle conferme. A quel punto molti altri nuovi obiettivi sembravano a portata di mano. Mi ricordo dei fisici asserire che la supersimmetria sarebbe stata scoperta in 6 mesi. 6 mesi dal 2012. Ma in realtà poi è arrivata una sorta di disillusione. Non solo i fisici sembrano in difficoltà nel trovare risposta alle loro domande, ma sembra quasi che non sappiano neppure bene come porre le domande. Insomma, la mia impressione è che voi siate in questo momento piuttosto infelici come comunità. Ci dice per favore cosa manca nel modo in cui voi avete immaginato l'universo? Cos'è che non torna?
You're right. I remember very well in 2012 when the Higgs boson was discovered and the excitement. And what was interesting was that the Hadron Collider and the experiments at CERN were being discussed by wider society in newspapers. You know, people who didn't have a background in science were still talking about, have you heard the news? They discovered this new particle called the Higgs. I don't know what it is, but it's very exciting and it gives us some understanding of the secrets of the universe. So from a science communicator's perspective, I think it was wonderful. It generated a lot of interest. But for physicists, yes, there was this hope that it would lead to, as you say, further discoveries and breakthroughs. I should say, of course, that physicists who were not involved in the experiment at the Large Hadron Collider itself, it would have been more exciting had we not discovered the Higgs boson, which may sound very, very strange to say, but it would have meant that there is new physics to discover. The Higgs boson was predicted over half a century ago by Peter Higgs and others, for which, of course, they won the Nobel Prize once it was discovered. And so it wasn't a surprise. We were sort of expecting it. It's another box you tick. Yep, Higgs boson, we have found it. Good, move on to something else. So it wasn't a surprise. What is surprising is that we haven't followed it up with further discoveries. As you say, this idea of supersymmetry, which is a mathematical description of the building blocks of the universe, would be very convenient if it were true, if nature behaved supersymmetrically. But we have found no evidence of that, and that is surprising. So it means that our picture of the universe, the picture of reality, of physical reality, is not complete. We don't know what dark matter is made of. We don't know what dark energy is. We don't know if we will ever reach a theory of everything, a theory that unifies all the forces and phenomena in the physical universe. So from 2012, when we're feeling very excited and encouraged that maybe the end of physics was approaching, now we've realized that maybe it's further away than we thought. I think that's a good thing. I'm not depressed about that. I feel frustrated that there are still questions we can't answers to, but at the same time it's exciting, because if we had all the answers, I think life would be boring. I wouldn't have a job, for example.
Fra l'altro, ricordo che nel 2012 l'annuncio della scoperta del bosone di Higgs è stato seguito in tutto il mondo da 1 miliardo di persone. 1 miliardo di persone che si chiedevano cos'è una particella fondamentale, cos'è questa particella, perché è importante per noi. E adesso? Cosa avverrà adesso? Beh, nella fisica ogni progresso deriva dall'interazione fra fisici teorici e fisici sperimentali. I teorici si pongono delle domande, magari osservando un fenomeno, e cercano di spiegare, di trovare una soluzione disegnando un modello, una teoria, e poi i fisici sperimentali devono mettere alla prova quel modello, quella teoria, inventando un esperimento che lo confermi oppure lo neghi. E a volte hanno successo, a volte non riescono a trovare una risposta definitiva, altre volte trovano qualcosa che costringe i fisici teorici a riaggiustare la teoria e così avanti, un progresso dopo l'altro. Solo che adesso la fisica ha bisogno di strumenti veramente molto costosi e ha bisogno di unire le forze in grandi collaborazioni internazionali. Ora la domanda è, visto che c'è un grosso dibattito anche nella comunità dei fisici, quale sarà il prossimo strumento di cui ha davvero bisogno la fisica? Cosa pensa che occorra? Un nuovo acceleratore di particelle più potente di LHC? Qualcosa di diverso, per esempio degli strumenti mandati nello spazio, o forse qualcosa ancora d'altro?
Well, my background in my research is in nuclear physics. And nuclear physics is somewhat distinct from high energy particle physics, which is what the LHC is for. Of course, there are nuclear physics experiments at CERN as well. There are other instruments there to do experiments in nuclear physics. And for me, in my area, in nuclear physics, theory and experiments have always been moving in parallel. So not always does the theorist propose a new hypothesis or a new equation or a new theory, and then the experimentalists have to go and check it. Sometimes sometimes experimentalists will do an experiment, they will gather data, they will see something interesting, and then the theorist comes in and tries to interpret it or develop a model that would explain it, and that way we make progress. You're right, in high energy physics, the work that's done at the Large Hadron Collider, we're not reaching the limit yet. There's still, I think, much more that will be done at the LHC and much more data that needs to be studied. But yes, if we want to move to the next stage, do we build a bigger collider? And of course, these machines are so expensive. Not one country can develop such a project. There have to be international collaborations. And even other science are then a little bit cautious about agreeing to something like this, because of course there is a finite amount of thing, and science is very wide and varied. And if you put lots into one project, then other projects, of course, will not get funding. But in particle physics, in astronomy, this is what's called big science, and it requires a lot of work. My view is that although I think it's good that we are thinking about new colliders, larger machines, I think the exciting developments will come from less expensive projects. Yes, we will have what's called the James Webb Telescope launch soon into space. This is the replacement for the Hubble telescope. It will be able to look out into the universe with much greater detail. That's very expensive, but it's been built now. It's happening. But there may be other much simpler experiments in smaller laboratories that will probe nature in very novel ways that don't cost so much money. I think we as scientists, physicists in particular, have to be more imaginative in thinking of ways of testing our theories, because a theory is only as good as the predictions it makes, and those predictions have to be tested against reality. It's no good in pretty maths. Beautiful mathematics, elegant mathematics is aesthetically pleasing for the theoretical physicist or mathematician, but it's not science unless it can be put to the test against observation. So we need new experiments, we need new observation, and I think we just have to be imaginative in how we find the way to do this.
Il progresso della scienza spesso è ostacolato da cose che non hanno niente a che fare con la scienza. È stato ipotizzato che la scienza greca sia stata fermata dalla fine del periodo ellenistico dovuto all'espansione dell'impero romano, e poi questo progresso delle conoscenze è stato in qualche modo portato avanti dalla cultura islamica e poi dal Rinascimento europeo e così via fino ad oggi. Ora, lei pensa che al momento ci sia qualcosa che minaccia il nostro progresso scientifico?
We live in, well, of course, we live in very dangerous times at the moment with existing with the coronavirus pandemic. But we also are seeing that there is this anti-science sentiment that seems to be spreading, often encouraged by social media, encouraged by polarization of opinions and ideologies. We see this in Europe, we see this in America, we see it in many countries around the world. And it does worry me that a rational worldview, which we have had since the ancient Greeks, and it may be that the golden age of Greece and the Roman Empire went into decline, the Islamic Empire rose, that went into decline, the Renaissance and the scientific revolution in Europe grew again with Copernicus and Galileo and Newton and so on. So of course we worry, it's also a finite period of enlightenment. we're going to in dark ages. I don't think so. I'm an optimist. So I'm not religious. I'm a humanist. So I have a positive attitude towards humanity, and despite all the negativity, and despite some can be very depressed about, our politicians, for example, I still feel that society in general understands just how important science has been in transforming our world, in health and medicine, in technology, in our understanding of nature. And I don't think we are now in a position to throw that away and move into some dark age of anti-science or irrealism and superstition. There has always been some minority of people who are suspicious of science, but I think the majority of people still value its worth for the world.
Torneremo sull'antiscienza più avanti, ma adesso vorrei parlare un po' di meccanica quantistica. Si dice che il premio Nobel Richard Feynman abbia detto: se qualcuno sostiene di aver capito la meccanica quantistica, allora vuol dire che non l'ha capita affatto. Non sappiamo mai quanto queste frasi famose siano state veramente pronunciate, ma almeno questa, diciamo, è rassicurante, almeno per chi come me purtroppo la meccanica quantistica non può dire di averla capita. Eppure la meccanica quantistica viene chiamata in causa per spiegare tutto quello che non capiamo, compresa il funzionamento della mente umana. In effetti, la meccanica quantistica ha già cambiato la nostra visione della natura, ma forse ci stiamo aspettando troppo?
No, I don't think we're expecting too much from it. Quantum mechanics has transformed our world more than probably any other area of science. You may think, of course, say this, he's a quantum physicist, he's promoting his area. When Feynman said nobody understands quantum mechanics, what he was talking about was we don't yet have a agreed upon interpretation of the meaning of quantum mechanics. Quantum mechanics is a mathematical theory which describes the nature of the microscopic world. Atoms, the particles that make up atoms, they behave in a way very different from the way objects behave in everyday life, the physics we learn at school, the physics of Newton and Galileo. So quantum mechanics is a new kind of mechanics. Well, I say new, it's been in existence for a century, but it's very powerful and it's very accurate. What we don't understand exactly how to interpret what is happening in the subatomic world. There are many different ways of interpreting it. Some physicists will say there are parallel universes. Schrodinger's cat box, the famous example, is dead and alive at the same time. And when you open the box, they will say in one universe, you will see a dead cat, but there will be a parallel universe, you see a live cat. It sounds like metaphysics. It sounds like fantasy. There are other interpretations which say it doesn't even exist. The cat doesn't exist until you open the box and you create reality. So, and I won't go into all the other. So Feynman was saying interpretations of quantum mechanics are still a confusion, but quantum mechanics as a theory, as a mathematical construct, it is very powerful, and we do understand it because quantum mechanics helped us develop all of modern electronics. Without quantum mechanics and understanding of the quantum world, we would not be having this discussion on our computers. So I think more to come. I think we haven't reached the end of the road, but we shouldn't deny that quantum has so far been a tremendously successful scientific theory.
Nel suo libro c'è un intero capitolo dedicato alle applicazioni della fisica. Abbiamo già nominato il GPS e noi giornalisti scientifici amiamo molto ricordare che il web è stato sviluppato al CERN di Ginevra. E questa è qualcosa che è molto facile da comunicare e in effetti voi fisici non dimenticate mai di citare le applicazioni della fisica ogni volta che cercate supporto per la vostra ricerca o semplicemente cercate i fondi di cui avete bisogno. Però non possiamo negare che le applicazioni non sono lo scopo principale della ricerca di base, lo scopo principale è la conoscenza. Ora, lei pensa che sia possibile avere un supporto per la ricerca e i fondi necessari senza citare le applicazioni della ricerca fondamentale?
I think it is possible, yes. In my view, in an enlightened society, seeking new knowledge is something that we should value for its own sake. We shouldn't have to always give a reason for the research. Why are you doing? I mean, when I do my research in nuclear physics, for example, some years ago, about 20 years ago, I published a series of papers, particular type of atomic nucleus, which had a strange structure. The particles that make up the nucleus, the protons and neutrons, were arranged in a very, very strange way due to quantum mechanics. It was fascinating. It was interesting. I was talking about it in many conferences. But if someone asked me, so what? Can this give me a new technology? Can it lead to a new type of a device or instrument? I'd say no, it's just understand something more about the building blocks of the universe. I think that, of course, you know, that funding societies and governments and countries have to fund many things: health, education, defense, business, running society. So science can't just say there's a group of people who are very clever with mathematics or in their laboratory, they're curious about the world, give them money to go and think about deep things which will not affect the rest of society. I agree, that is not a good argument to make. However, we know throughout history, the more we understand, the more knowledge we acquire through science about our world, the better we can make it. There are applications that come from the science we discover, but we shouldn't always have to carry out the science with that end goal in mind. Michael Faraday famously was working in the 19th century on electricity and magnetism and coils, and he wasn't thinking, I am going to build the electric motor, I'm going to develop electricity. He was just fascinated, but because of his fascination, his curiosity-driven research, that led to a transformation of our world. So we should keep gaining knowledge for its own sake, and technological applications will inevitably follow. Maybe not the next day, maybe 10 years, 50 years later, but that knowledge will be shown to be useful at some point.
In effetti è stato detto che non si sarebbe mai potuto ottenere la lampadina migliorando all'infinito la candela. Per ottenere la lampadina ci vuole un completo cambio di punto di vista, che è quello che solo la ricerca fondamentale può dare. Ora, è difficile fare una classifica, ma nella sua opinione qual è la applicazione di cui dobbiamo più essere grati nella ricerca fondamentale in fisica, almeno negli ultimi anni?
If we're talking about the last few years, then I have to think about this a little bit, because I think to say what do we owe physics is a too big a question. What do we owe chemistry? What do we owe engineering? You know, all of the sciences, genetics, computer science, medicine, have been so, they overlap and they have affected each other and helped us develop new ideas and new technologies that have made our lives better. But in terms of fundamental physics, in the last few years, I think probably what we will find, although it's still in development, I still think it's the next stage of our understanding of the quantum world. So quantum mechanics has, over the last century, in the 20th century, allowed us to understand the nature of matter, the nature of how electricity moves through materials and helped us develop modern electronics. So semiconductors, the silicon chip, the computer. Now you look at your smartphone, your iPhone, everything, it's full of quantum mechanics. You know, without quantum mechanics, we wouldn't have these devices. That was quantum 1.0. We have quantum 2.0 in the 21st century. And that will, I think, transform society. And we're now working on developing, for example, quantum computers, quantum cryptography, even science fiction ideas like quantum teleportation. So it'll transform our communication, it'll transform some of the problems we can solve in society, problems which may be too difficult for a normal computer, even the most powerful supercomputers. A quantum computer may be able to tackle these problems. So I think fundamental physics, I would say the next generation of quantum ideas are the most important.
Grazie professor Al-Khalili, l'intervista purtroppo sta volgendo al termine, purtroppo per me, ma vorrei tornare sull'antiscienza perché è un tema molto caro e vicino al CICAP. Ora, quando parliamo di antiscienza, tendiamo a pensare che chi la sostiene viva nel passato, in epoche remote, ma io non credo che sia così, perché in effetti anche nelle epoche remote c'è sempre stato qualcuno che cercava di capire la natura, l'universo, il mondo e così via. E quindi è come se in realtà queste persone ignorassero la storia della scienza, la storia dei progressi scientifici che ci hanno portato fino ad oggi. Così siamo ancora alle prese con domande che sono state risolte da secoli, almeno da decenni. Per esempio, la Terra è piatta? Tutti gli esseri viventi sono stati creati in 6 giorni, come detto nella Bibbia. O ancora, i vaccini funzionano? L'omeopatia è meglio di un placebo? Ora, a conti fatti, sembra che la scienza abbia cambiato la nostra vita, ma non sia riuscita a cambiare le nostre menti. Ed è stupefacente perché cambiare le menti è qualcosa che può riuscire molto bene, per esempio, a una predicazione religiosa, può avere effetti per millenni, oppure anche a una filosofia. Per un certo periodo di tempo può riuscire anche a una visione politica, pure a una pessima visione politica. Quindi, qual è il problema della scienza? Perché non riesce a cambiare il nostro modo di vedere le cose, anche se alla fine ci fornisce in genere le risposte più semplici.
You're right that this isn't a new problem. We have always had people who are suspicious of science, suspicious of some of the conclusions about our world that science is showing us. There have always been people who thought the Earth was flat, even though, as you say, even the ancient Greeks could tell just from the angle of the sun, they could tell the round. I think, obviously, one of the problems is that it's the use of the technology that science has allowed, which encouraged people to shout more loudly against science. So social media, for example, has helped amplify some of these anti-scientific ideas. You know, the flat Earth society is growing these days, despite all the evidence we can show that the world isn't flat. That, I think, that sort of idea is, I find it amusing. And the people who believe the Earth is flat are not stupid. They believe they are thinking scientifically. They believe they are looking for evidence and testing a hypothesis. And they're saying, look, we're doing science as well. But of course, they're testing the evidence that they want. That's not so, that's hard, I think. What is much more of a danger are those who, for example, don't believe in scenes, you know, or don't believe that the Earth's climate is changed by our actions, and that can do real damage, particularly if politicians or people in power also adopt that attitude. I think for me, one way of tackling this is not just to explain science, not just to talk about the Higgs boson or the latest discoveries in astronomy or how weird and mysterious quantum mechanics is, but to get across the scientific method, how science works, what scientists do that persuade them that what they're discovering is some truth about objective reality. Trying to get across that not all truths are equal. You know, you cannot say my opinion is as valid as yours, even though you are an expert and you have evidence and you have spent many years studying something. I read something on YouTube, or I've thought about this while drinking my beer, and my opinion is equal to yours. We have to show that in science, you have to, first of all, be prepared to change your mind. And people don't like changing their mind. When you have a fixed view or ideological point, it's very difficult to persuade you, to give you new evidence to change your mind. Psychologists understand this. But in science, we don't work like that. In science, if my theory is proved experiment, I have to abandon that or improve it or change it in some way. So understanding the importance of evidence, being able to change our minds, being prepared, admit our mistakes, admit when we're wrong, because that's the way we learn, and being able to listen and debate and discuss and reach consensus. One of the things about modern society is that we have lost the ability to see the gray between the black and white. Every issue has to be polarized. If you are not 100% with me, you are my enemy. Particularly on social media. So we don't do that in science. In science, we always have to move and say, well, okay, you have a point and you have a point, but the truth may be somewhere between. So all these ways of how we do science, I think we have to get across to wider society, because on the whole, I feel positive about humanity. You know, people are not all evil. What they think they're doing the right thing, they believe they are being good. We just have to show in a non-judgmental way, in a non-arrogant way, that the way science progresses is careful, and it's really trying to seek a truth that's out there. This cultural relativism idea that we've had is something I find very disturbing, that somehow everything is relative, all views and opinions are valid. Yes, we have to listen to each other. Yes, I'm not 100% right and you're 100% wrong. But, you know, there is also a reality out there that we scientists are still trying to understand.
Grazie professor Al-Khalili per il suo tempo, per la piacevole conversazione.
Thank you.
E a tutti voi che ci avete seguito, restate con noi perché il CICAP Fest continua. Grazie ancora.